Okay, today let's start off with a quiz. This quiz is on the material that we learned in the last chapter. Okay, so you'll see it's very similar to a question that we covered at the end of last class. You are looking at miles per gallon of Toyota Highlanders, and you have a bunch of data set for 20 different cars and their miles per gallon. Here you're assuming that you don't know the standard deviation of all vehicles, Toyota Highlanders. So sigma is unknown. Okay, since sigma is unknown, then you have to find out what is the standard deviation of x bar. Okay, which is S of x bar okay, and then based on that you have to find out the margin of error, M, right? And we know that to be either the Z critical or the T critical value. So either Z critical times this value, or T critical. So it just means you have to choose the right distribution here. It's going to be one of these two as the margin of error. Right, this term, the standard deviation of x bar, we've also called it the standard error. Okay, so once you find the margin of error, then you have to find the confidence interval. That's 95%. And so the confidence interval is x bar plus or minus your margin of error that you find in the previous question. And then based on that, you make a conclusion if the results of this experiment is consistent with the claim that mu is equal to 27 miles per gallon. Is that claim correct, or is that wrong based on this confidence interval? So once you do all this, again, put it into a Word document and upload the answers onto the submission for quiz 3. Thank you. And now we move on to hypothesis testing. Okay, in this chapter we're going to cover hypothesis testing. And what do we mean by hypothesis testing? So if you go back to the previous question that we just did for quiz 3, this question, you see at the end we had a hypothesis that if the average miles per gallon of all Toyota Highlanders was 27 miles per gallon or not. And we constructed a confidence interval to prove if that claim can be correct or not. Okay? So similarly, we're going to do this exact process, but now not through the use of confidence intervals, but rather hypothesis testing, and we're going to define probabilities to help us come to that conclusion. So first we're going to set up hypothesis, okay? Null hypothesis and alternative hypothesis. This null hypothesis is denoted as H0, and alternative hypothesis is denoted as HA, or you can also use H1. Okay. And then we'll look at z-tests, z-hypothesis tests using the z-distribution. when you're trying to do a test on the mean. Again, that assumes that sigma is known. Or we're going to learn t-test for, again, the mean when sigma is unknown. We're also going to learn a z-test for the population proportion, right? Remember, proportion is p and the means are mu. We're also going to learn about the chi-square distribution, and that's going to help us do a test on the variance, right? The population variance being sigma squared. So why do we need hypothesis testing? So let's kind of look over it through an example. We've seen that there is randomness involved in all the statistical tests that we do. Now we have to find out if a certain conclusion that you reach from a test, now, is that because of random chance, or is that really saying that something is wrong with a process? Okay, so for example, suppose you're in charge of quality control in a food company. You are randomly sampling 4 packs of cherry tomatoes, each labeled half a pound. That's 227 grams. You take 4 boxes and the average weight is 222 grams. Well, you don't expect it to be exactly 227 grams because there is randomness involved, right? So that difference, well, is that difference simply due to chance, some randomness? Or is that really saying that that calibration machine that you're using really has some issues, and so you should not be tagging your products with the half a pound tag? So do we need to revise the packaging? And that's a big question to ask. In fact, if you mislead customers, you can get sued, and so you're trying to protect yourself to make sure that you're giving accurate information. That's why we need hypothesis tests. Okay, so it's a statistical test on significance that is dependent on some probability, and you're deciding on the validity of a hypothesis. Okay, so in statistics, a hypothesis is basically what you assume to be true. Okay, so for that, you want to know in this example if we need to calibrate the machine. And that same question can therefore be reorganized to say, is the population mean, mu, of all cherry tomato packages equal to 227 grams? Right? So the question is mu equal to 227 grams? And we need a way to prove this. Okay. So we define null hypothesis and alternate hypothesis. This is very important to understand. The null hypothesis is your unbiased hypothesis without a bias. Okay, what does bias mean? Bias means you're taking a side, you're picking a side. The null hypothesis has to be one where you're picking no sides. Okay, so it usually has a statement that there's no difference or no effect. Okay, and the alternative hypothesis is that yes, you're picking a side. What you assume to be true is actually an alternative hypothesis. It's your conception that you already, a preconception that you already hold about your test. Okay, so null hypothesis is unbiased. Alternate hypothesis is biased. Okay, so in this example, what do you think a null hypothesis should say? H naught. Well, if you want it to be unbiased, well, then you're going to assume that the null hypothesis says that the average weight mu is 227 grams exactly, right? You're not picking a side, you're not giving it any preconception. You're just assuming that what is told on the package is true. Okay, you're not picking any sides. Whereas in the alternate hypothesis, you're saying mu is not equal to 227 grams. It's either larger or smaller. Both could be true. And so you're saying it's not equal to, well, then you're picking a side. You're saying the packaging is wrong. Okay, so this is biased. So therefore, the alternate hypothesis states that mu is not equal to 227 grams. Okay, that's how you write hypothesis. Now, this is just one example of an alternative hypothesis. While the null hypothesis will always be equals to, when we're doing hypothesis testing, it'll always be equal to a number. Okay. The alternative hypothesis can be two-sided or one-sided. For two-sided, it's just a not equals to. So having greater than or less than breaks the hypothesis. Okay, so if a number is greater than, then it's going to be true for the alternate hypothesis. If a number is less, then it's also going to be true for null hypothesis. Whereas if you do a one-sided test, okay, and if you hold it for, the alternative is for less than, well then a number greater than will not break this will not break the null hypothesis, and therefore will not make alternative hypothesis true. Conversely, if you have a number that is less than, and yet here you're checking for mu greater than a number, then again your null hypothesis will not break, and therefore your alternative hypothesis will not be true. Okay, so for one-sided test, you have again equality for the null hypothesis, but the alternative hypothesis tests for one side of it, so it's either less than a number or greater than a number. Okay, so for example, if you were looking at, let's say, FDA test for generic drugs, has an absorption extent similar to known other absorption brands, and in both cases, if you have that it's higher than or lower than would break that chain, then you have a two-sided test because you're just testing for if they're equal to each other or if they're not equal to each other. It's two-sided. Whereas if you're looking at a company, let's say, tests the mean volume of tea in their bottles as 500 milliliter as stated, well, then the company would be more concerned if the bottle contains less than what's advertised, right? So there you're testing for, again, if it's equal to or if mu is less than 500 milliliters. Okay, so it's very important to first set up the correct hypothesis. That's the step one, okay? That's very important. Step one for hypothesis testing is set up the correct hypothesis. Okay. Once we've learned how to set up hypothesis, then we have to figure out what test to do. Okay. So if you have a known sigma, right, just like we talked about with confidence intervals in the last chapter, chapter 8, here if you know sigma, right, population standard deviation, okay, just to remind you, this is population standard deviation. So if you know the population standard deviation, then you're going to use z-test. Okay, the z-distribution. And to use the z-test, you're going to calculate the z-statistic. Okay, this is called the test statistic. Okay, and we've looked at this formula before, right? Remember when computing your z-score in chapter 7 with the means? Well, this is what you used, right? This is your the z-score. Excuse me. So this is what we compute from the data set. Okay, Again, to remind you, this is different from Z critical that goes in a confidence interval. Okay, Z critical you get from the confidence level. Okay, Z statistic you get from the data, and Z critical you get from the confidence level. Right? From the confidence level you get alpha, and that alpha is what's used in computing Z critical. Okay, so for example, you're looking at the hypothesis in that cherry tomatoes example of the mean being 227 grams, and the alternative being that it's not equal to 227 grams, and you found out that the average of the 4 boxes you weighed is 222 grams, so X bar is equal to 222 grams. Okay, well, based on that, what is the probability of you drawing another random sample so that it proves that your null hypothesis is true? To get that probability, we compute something called the p-value. Okay, you're going to see this p-value over the entire semester over and over again. This p-value basically shows if a random variable by itself, the randomness in your data set, could lead to account for the difference that you observed. Okay, so if you have a small p-value, that means that the difference that you observed is just by some random chance. Okay, so if a small p-value means that the probability is very small that it is due to some random chance. Therefore, you have proved that there really is something wrong with the process. Okay, so small p-value means we reject our null hypothesis. That means that the population is significantly different from what we originally thought our null hypothesis to be true. Okay, so small p-values means there is strong evidence against the null hypothesis. So how small is small? So p-values, if you remember now, if you have a distribution, say the Z distribution, then where you cut it, the Z statistic value is on the x-axis, okay? And the area to the right-hand side is the p-value. Okay, so this is Z statistic, and so is this is negative Z statistic. Okay, and then this area to the right-hand side is the p-value. If you have a two-sided test, right, the p-value is on both sides, and when you sum them up, you get the total p-value. If you have a one-sided test, let's say a less than, then the p-value is just on one side. Okay. And if you have a right-sided test, again, the p-value is just on the right-hand side. And if you have a two-sided, again, the p-value is on two sides. And again, on the x-axis, these are all Z statistics. Okay, these are all Z stat values. Now, what we do is actually compare this p-value that we get to 0.05 typically. Where does that 0.05 come from? That 0.05 is in fact what is alpha. Remember we talked about alpha in the confidence interval section, right? It was 1 minus the confidence level over 100. Right, so if it was 95%, then it would be 95 divided by 100, 0.95, and then 1 minus 0.95 would give you 0.05, which would be alpha. Right? So you compare your p-value with alpha to make a conclusion. Okay. So the p-value proves, based on the z-statistic, if you can reject your null hypothesis or fail to reject your null hypothesis. Okay, so again, to summarize, we can have one-sided tests, right or left-handed, and we can have two-sided tests. The p-value for the two-sided test will be summation of the area on the right-hand side and the area on the left-hand side. Okay, so you have to double it for two-sided test. Whereas for one-sided, it'll just be the area on one side. So in this example of cherry tomatoes, we had the hypothesis that mu is equal to 227 versus it's not, and x bar equals to 222. That's what you got your sample weight as. Assume that you know sigma. Okay. Assume known sigma. And that is equal to 5 grams. Okay, and a sample size is 4. Well, then I can compute my z-statistic. I can compute my z-statistic as 222 minus 227 divided by sigma over square root of n and get -2. Okay, then I can go to Minitab and put in z-stat value. Okay, so let's do that. Okay, I can go to graph, probability distribution function, view probability. Okay, so same place we've been coming to find out probabilities. Again, we're working with z values, so you leave it as normal with mean of 0 and standard deviation of 1. Here you have the actual z value, right? So the x is generic, remember. So here you have the value. Anytime you have the actual z value or t value or chi-squared value, you check this. And we want it to be two-sided, right? Because it's a two-sided test that we had, right? It's not equals to. And we found a z value of -2. So we're going to put in -2. When we click OK, you're going to see that we get one side of the area as 0.002275, the other side as 0.002275. When you sum them up, right, you get somewhere around 0.045. Okay, so you see that that's what we have when we even do this with the table. Okay, so you have 2.28%, right, which is 0.02 0.0228. Right, 0.0028, that's 2.28%. So when you add them up, you get 4.56%. That is your total p-value. Okay, and we compare that with alpha, right? If, let's say, we were doing this test at 95%, well then alpha would be 5%. Okay, and so the probability of you rejecting the null hypothesis is going to be 4.5%, which is less than 5%, and therefore we will reject a null hypothesis. So the machine does need recalibration. Okay, so p-value is less than or equal to alpha. Therefore, we reject H naught, which is the null hypothesis. That means we accept H1. Okay, accepting H1 means that mu is not equals to 227 grams. Therefore, the machine needs recalibration. Okay, so a good rule to remember through all of this is exactly this. When this rule will never change in your life, ever, and whenever you're doing statistical comparisons. Okay, when p-value is less than alpha, we reject our null hypothesis. When p-value is greater than alpha, we fail to reject our null hypothesis. Okay, in failing to reject null hypothesis, it doesn't tell you to accept not the same as accepting H naught. This, however, is the same as accepting H1, the alternative hypothesis. By rejecting the null hypothesis, you are accepting the alternative hypothesis. But by failing to reject the null hypothesis, you're not accepting H naught. You're simply saying the test is inconclusive. You didn't learn anything from the test. So go for getting another sample and trying it out again. That's the takeaway when you fail to reject. You didn't learn anything from the test. Okay? So in the case of this cherry tomatoes example, we found that the p-value is 4.56%. So at the confidence level of 95%, you rejected the null hypothesis. So you found that the machine does need recalibration. So the p-value was significant. But if you had put alpha at 1%, right, which means the confidence level is 99% here, and here the confidence level was 95%. Right, so if you had made the confidence level 99%, leading to an alpha of 1%, well, then the p-value would have been greater than alpha, and you would have failed to reject the null hypothesis. So p-value would have been insignificant, not significant, and therefore wouldn't have learned anything from the test. Okay, so by changing the confidence level of the test, you can get results that either mean something or don't mean anything. Okay. Now, what does alpha really mean? Or what does the confidence level really imply? Well, the confidence level leads to you getting alpha, right? And alpha is 1 minus the confidence level divided by 100. This alpha is the probability of making a type 1 error. What do I mean by that? Type 1 error is an error that occurs when you reject the null hypothesis when in fact the null hypothesis was true. Okay, so by putting, let's say, alpha, for example, putting alpha at 5%, right? Now you're saying you have a 5% probability of rejecting null hypothesis when in fact the null hypothesis was true. So you're taking a 5% risk of being wrong. Okay, there's also a type 2 error, and we won't go too much in details about the type 2 error, but the type 2 error says when you fail to reject the null hypothesis when in fact the null hypothesis was false. Okay, that is the type 2 error. This part I want you to remember. So fail to reject H0 when H0 is false. That's type 2 error. Type 1 error is rejecting H0 when H0 is true. Two different errors. Okay, this is directly related to type 1 error is directly related to alpha. Okay, type 2 error is in fact related to a quantity called beta, but we won't cover too much on type 2 error, so you won't have to worry about it. Okay. So alpha is what is set by the confidence level. That's the risk, that 5% chance that you're willing to take of being wrong. Okay, so alpha could be 5% all on one side, or alpha could be two-sided and split that 5% or 1% on two sides. Okay. And the tables can then be used to find out the appropriate Z critical values. Again, this is Z critical, and this is positive Z critical. Okay, it could be used to find out the critical values, and then you can perform your hypothesis test. So the steps for hypothesis test then can be summarized. You first state the hypothesis. Okay, null hypothesis and alternative hypothesis. You figure out what alpha is. What is alpha, right? The significance level. That's usually just the confidence level. Once you find out the confidence level, you just set alpha. Typically, if a confidence level is not mentioned in your course or anywhere else, you will assume that the confidence level is 95%. Excuse me, sorry, typically. Okay, unless it specifically the question states a different confidence level, then use that. Then you will calculate the test statistic. Okay, so Z stat x bar minus mu divided by sigma over square root of n. Then you will find the p-value, and if p-value is less than alpha, you will reject a null hypothesis. If p-value is greater than alpha, you will fail to reject a null hypothesis. Okay, now you could also compare Z statistic with Z critical and come up with the same conclusion. So let me draw that picture for you. Suppose you have Z statistic, okay, and this area on the right hand side of Z statistic and this area on the left hand side of the negative Z statistic. What are those areas? These two areas combined is the p-value, right? Now, suppose I draw an alpha, which is the blue shaded area, and it's somewhere down here, area to the left of that, and you have an area to the right of that. Okay, so if I'm talking about Z critical here and negative Z critical here, well then what are these areas? These two blue areas combined is alpha. Okay, so by saying that when p-value, which is the red area, is going to be more than the blue area, so this thing right here, you will fail to reject the null hypothesis. Therefore, you can say also that when Z statistic is on the inside of Z critical, okay, so also if negative Z stat is bigger than negative Z critical, or positive Z stat is smaller than positive Z critical, in this example exactly how I have it, right? Z stat, the negative Z stat out here is bigger than negative Z critical, which is out here. The red line is on the inside of the blue line. Well then what should happen? Your p-value is larger than your alpha, which is this case. That's exactly what I've drawn here. So you would fail to reject H naught. Okay, so you can in fact make the same conclusion without using p-value and alpha, just by using Z statistic and Z critical. And on the other side, if negative Z stat is less than negative Z critical, so a picture that I haven't drawn, where let's say if the blue line was in here, right, past the Z statistic, the blue line was out here and the area to the left of that, well then Z statistic would be on the left hand side, the negative Z statistic would be on the left hand side of negative Z critical. So if this blue moved inside, then negative Z stat would be less than negative Z critical, or positive Z stat would be greater than positive Z critical, right? This blue line would move inside, so the positive Z stat would be on the right hand side, so more than the positive Z critical. Okay, in that case, alpha, the area to the left hand side of Z critical, would be more than the p-value, which is the red area. The blue shaded area, once we move this in, would be more than the red shaded area. So therefore, p-value would be less than, the red would be less than the blue. Red is p-value, alpha is blue. So red would be less than the blue, therefore we would reject H naught, our null hypothesis. Okay, so you can see that we make the same conclusions with comparing Z statistic with Z critical as you do with p-value and alpha. Okay? Just by comparing Z statistic with Z critical, you can make the same conclusion as you do with comparing p-values and alpha. Okay. Now, there's a third way of also getting to a similar conclusion, and that only works if the test is two-sided. Okay? Only works if the test is two-sided. When the test is two-sided, you can also do a hypothesis test using a confidence interval. And that's in fact what you did in quiz 3. Okay, if you go back and look at quiz 3, you did a confidence interval on the miles per gallon, and then you saw if 27 miles per gallon, what you hypothesized about, fell into that confidence interval or not. And if it did, you said the claim was true. If it didn't, then you said the claim was false. That's a hypothesis test. So in this cherry tomatoes example, if you set up a confidence interval, remember, confidence interval is x bar plus or minus z of alpha by 2, right, what we call z critical, times sigma over square root of n, right? So you know x bar as 222, z critical, well, what is alpha? Alpha equals to 95% is confidence level, right? So alpha is equal to 5% or 0.05. So you have to look up z of 0.025. Remember, because it's two-sided, you have to divide alpha on both sides, right? This is alpha divided by 2, so 2.5%, and this would be alpha divided by 2, right? So 2.5% or 0.025. When you look that up, you get z of 0.025 equals to plus or minus 1.96, and that's the z critical, times by sigma. You already remember from the previous example, sigma was 5, divided by square root of n was 4. That gives you a confidence interval of 222 grams plus or minus 4.9 grams, which then works out to be the confidence interval 217.1 grams to 226.9 grams. Okay? Now, even though 227 is very close to that upper limit, you still see that 227 is outside the confidence interval. Okay? And therefore, we reject our null hypothesis. Okay, so a takeaway is, if confidence interval does not contain the population parameter mu, what you hypothesized mu to be, mu naught, right? So your initial hypothesis was that mu equals to some value. I'm going to call it mu naught, some value, right? If it's 0.86, it's 0.86. For the cherry tomatoes, it was 227. So I just call it mu naught, some value, to be generic. And mu is not equals to mu naught, right? If that was a hypothesis, well then, if the confidence interval does not contain this number, mu naught, then we reject the null hypothesis, H naught. And if it contains it, if it does contain it, so if the confidence interval does contain mu naught, then we fail to reject H naught. Okay. Okay, so 3 ways of exactly doing a hypothesis test. The third way only works if the hypothesis test is two-sided. Okay, if it's one-sided, such as H1 being mu is less than mu naught or greater than, these cannot be done by confidence interval. Okay, this cannot be done by confidence interval. Has to be two-sided for you to deal through a confidence interval. The benefit, though, however, of using the p-value is that the p-value tells you how strong of evidence you have to reject the null hypothesis. Okay, so as p-value starts to decrease, you'll see it gets very strong evidence towards rejecting the null hypothesis. So at 10%, p-value being less than 10%, you have some evidence. So if your confidence level was 95%, which is pretty sure, then you would not reject your null hypothesis. Now at less than 5%, yeah, you got some strong evidence to reject the null hypothesis, and you would at 95%. At less than 1%, well, then you would reject it at, you're 99% sure of rejecting the null hypothesis. At less than 0.001, you're 99.9% sure that you're going to reject your null hypothesis. So p-value is a measure of how strong or how sure you can be of your results. Okay, so let's do a question. You're looking at who is an author. Okay, and you can decide that based on some statistics that's taken about a poet whose average is 6.9 new words in every poem that they write. That's their historical average. Okay, so you want to set up your hypothesis. Okay, and that's mu naught is, sorry, h naught is mu is equal to 6.9 and h1, well, we have to find out if it's two-sided or one-sided. So you know standard deviation, sigma is 2.7, you know mu is 6.9. He says 5 new sonnets has come to life, so you know this is n, sample size. And you know the new sonnets contains an average x bar equals 11.2. We expect poems by another author to contain more new words. So to see if we have evidence that new sonnets are not by our poet, we test. So we expect them to have more new words. That means you expect mu being greater than 6.9 as the alternative hypothesis. Okay, so now that you have your hypothesis set up, we can find z stat. Okay, x bar minus mu divided by sigma over square root of n. Right, x bar is 11.2 minus 6.9 divided by 2.7 over square root of 5. And this comes out to be 3.56. Okay, now to find p-value, we have to go to Minitab. So to find the p-value, we go back to graph, probability distribution plot, view probability, right, same space. Again, we're working with the z-values. We already have our z-value from the question. Z-stat is 3.56. You want shaded area. You have the z-value, and what kind of a test is it? It's two-sided. It's one-sided with a right-hand side, right? So greater than. So you want to pick the greater than side, right? The right-hand side. And you found out that the value is 3.56. You click OK, and Minitab gives you a p-value very, very close to 0. Okay, anytime students get a p-value of 0, they get worried that that's not correct. That's great, actually. Okay, so p-value of almost 0, 0.0002. Okay, so that means from Minitab, sorry, pen, right, from Minitab, we get our p-value equals 0.0002, right? So then what does that tell us? P-value is less than equals to alpha, right? Alpha of 5%, 0.05, right? Because 0.0002 is less than equal to 0.05. Therefore, we reject H naught. And this proves that these new works are for new poets. So this proves new poems belong to new poets. Okay, and you could do this exactly same way with Z statistic and Z critical. So if you were to write down Z critical, right, if you were to write down Z critical, well, at 95% confidence, right, it's a one-sided test, so you won't divide, you won't divide alpha by 2, you just have alpha on one side. So this would be 0.05, and that would be plus or minus 1.645. How did I find that? From Minitab. Right? Remember, to find out Z critical, we go to that same place, probability distribution plot, view probability. But now, instead of having the actual Z value, you want to find the Z critical value based on some probability. You want right hand side of it, right? It's larger than, and you know your probability alpha value is 0.05. So you give that and you get 1.645. Okay, and so since I know my Z critical is 1.645, in fact in the positive side of it because it's one-sided, and I know my Z stat is larger, so since Z stat, the positive Z stat, is bigger than positive Z critical, if you go back in your notes, in this chapter, you'll see that we said in that case we would reject H naught and therefore accept H1. Okay, that proves that it belongs to the new poets. Okay, why don't we try another question? You're looking at wine products, and it says that there is an issue with the smell of it if it has a certain chemical in it. Okay, and the literature has 25 micrograms per liter as the threshold. Okay, so our hypothesis then is mu equals to 25 micrograms, and alternative is mu not equals to 25 micrograms. Okay. Now, if you read this a little bit differently and thought it was one-sided, then you would change this alternative hypothesis to be one-sided. But for now, let's just assume that it's two-sided. Okay, so I have these values. Now, I need to compute z statistic. Right? That's x bar minus mu divided by sigma over square root of n. What is my x bar? Well, it's the average of these 10 numbers. So let's find the average. 31 plus 31 plus 43 plus 36 plus 23 plus 34 plus 32 plus 30 plus 20 plus 24. Divide by 10, and your average is 30.4. Okay, and our mean that we are hypothesizing is 25. It says assume sigma is 7. Okay, so 7 divided by square root of 10. So that's 30.4 minus 25 divided by 7 divided by square root of 10. Okay, and you get a z value of 2.44. Okay, so 2.44. Then we just have to find the p-value. So again, back to Minitab. So back to graph, probability distribution function, view probability. Right? Now we have the z value and we're looking at it as two-sided. Right? It was two-sided. And our z value was 2.44. And we find out that the probability on each side is 0.0073. You got to add them up. Right? And you get a p-value of 0.015. Okay, so from Minitab, we get p-value of 0.015. So at alpha equals to 0.05, p-value is less than equal to alpha. Therefore we reject H naught. Therefore we accept H1, that the mean is not 25 miles per gallon. So is the literature accurate? No, it should be updated. Okay, that brings us to the part when sigma is unknown. Okay, and just like we saw before, we had to use an estimator. When sigma was unknown, we had to estimate sigma with the sample standard deviation S. Okay, and using that S meant that we would have to use the t distribution instead of the z distribution. Okay, so when sigma is unknown, we are going to use the t-test when we are testing for means, the mean, mu. Okay, so we'll use the standard deviation of the sample S, and we're going to use t-statistic, t-stat, that's defined as x bar minus mu S over square root of n. Notice that the only difference between this and z-statistic is in z-statistic it was x bar minus mu, same numerator, it's just the denominator had sigma over square root of n. Here you have the sample standard deviation. Okay, and the other thing is the t-distribution. Okay, so t-distribution is dependent on sample size. Its dependence is on something called the degrees of freedom. Okay, and we'll use df to denote that. And that degrees of freedom for a single sample t-test is n minus 1. Okay. So the steps are very similar. You define a hypothesis, just like you did, right? Mu equals to mu naught, and alternate hypothesis, mu either not equals to mu naught, or you can have greater than, or you can have less than, right? And then you compute t-statistic as x bar minus mu naught divided by standard deviation of the sample divided by square root of n. And then you find either the p-value based on that t-stat and compare with alpha, or you compare it to the t-critical value that is dependent on sample size, and that sample size dependence is on degrees of freedom with n minus 1. Okay, so you compare it to t-critical, which is, if it's two-sided, it's alpha divided by 2 and the degrees of freedom, and you make your conclusion. Okay, so very similar. Compute t-statistic, find the p-value, compare p-value with alpha, make your conclusion. If it's two-sided, make sure you add up the two probabilities to get the total p-value. So let's look at an example. You're looking at the sweetness loss for a new cola drink that came out, and alpha is 5%, so confidence level of 95%. You're testing if there was a positive value in the sweetness loss, i.e. there was a sweetness loss. So mu is bigger than 0, so it's one-sided. And you have 10 samples, 10 different tasters that tasted your product. If they gave it a positive number, that means there was some sweetness loss. So loss, 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 loss. They gave it a negative number, that means there was some sweetness gained. Okay, so you have a bunch of different values, and you know the average of it. Okay, so you know x bar. You know the standard deviation of this sample, so you know S. And you know the degrees of freedom is 9, so you know df. Okay, so you can go ahead and compute t-statistic. So x bar is 1.02 minus our hypothesized mean, we're guessing it to be 0, divided by standard deviation of all your sample points. You know, this standard deviation you can get either by computing it by hand, or you can plug it into Minitab. Just go to display descriptive statistics, and you'll find out the standard deviation, the mean, and anything you want typically will be under there for a data set. Right? You just type in these numbers. Okay, so you type in the numbers, then you go to stat, and then you go to basic statistics, and then you go to display descriptive statistics. And you put in the variable that you want to put in. So in this case, here you put in sweetness loss. That variable, right, that column of data that you typed up, and Minitab will give you back the mean, the standard deviation, sample size, all of that information. So once you have that, you can exactly go ahead and compute t-stat. Right, then you go to Minitab, put in a value of 2.7, and then Minitab will give you back the probability. And remember, it's one-sided, right? So it's 2.7 is the t-value. So you have to choose the right-hand side only, right? Because it's one-sided. And so you would find out the p-value. If you were doing it with a table, you would exactly read it off in between, but let's just do it by Minitab. So we would go back to our favorite place, probability distribution plot, view probability, keep it all the same. Actually, no, here we're talking about the t distribution, right? We're not working with z anymore. So that's what you have to be careful about. Here we're working with the t distribution. So we have to change it to t. Degrees of freedom, see, it's now dependent on sample size. Degrees of freedom is n-1, so we said that's 9, so we put in 9, and we have the t-value, and we are choosing the right hand side, right, and that t-value is 2.7. Click OK, and Minitab will give you back the probability, the p-value on the right hand side, 0.01. Okay, so based on this, based on Minitab, we know p-value is exactly equal to 0.01. See, in the tables it's very hard to approximate because the numbers are every certain intervals. So you know 2.7 falls in between these two numbers, so the p-value, corresponding probability, is somewhere between these two numbers, but you don't know exactly what it is. If you do it in Minitab, Minitab will give you the exact probability, and it was 0.012. Okay, and since you know p-value is less than equal to alpha, at alpha of 0.05, right? P-value is less than equal to that, therefore we reject H0 and accept H1. Okay, so there is a significant loss in sweetness on average following storage. Okay, just like a z-test, t-test, only difference using sample standard deviation here and the t-distribution. Okay, this little table kind of summarizes for you, you can pause it here if you like, the steps that you may want to take if you are using the critical value, if you're using t-stat with t-critical, and here they denote t-critical by t of alpha, or t of alpha by 2 if it's two-sided, right? And then they compare it with t being t-stat. Okay, so if your t-stat is outside t-critical, you make a certain conclusion and so on. And they make the same conclusion with p-value. So if you understand this table, you'll see how comparing t-statistic with t-critical is exactly the same as comparing p-value with alpha. It's just p-value and alpha is a comparison of areas, which is the area underneath the curve. There's a comparison of probabilities. P-value is a probability, alpha is a probability. Okay. Whereas when you're comparing t-statistic with t-critical, it's just comparison of values on the x-axis. That's the only difference. But essentially, you're doing the same thing. One is comparing the area underneath the curve, one is comparing values on the x-axis. Okay, so as a caution, you should be careful when you're using the t-distribution. Outliers can definitely affect your data set. So as a general rule of thumb, when you are using n less than equal to 15, the data should look at least somewhat normally distributed. When it's between 15 and 40, it's okay to have a little bit of a skewness, but not really too many outliers for you to use the t-distribution. When it is above 40, then the t-distribution is going to be valid no matter what. Your data is going to be somewhat the sampling distribution of the mean is going to be somewhat normally distributed, irrespective of any outliers or skewness. Okay, so essentially when you are n greater than 30, you're in a safe zone to use the t-distribution. You have to be careful about outliers, but you're okay to be okay about not worrying about too many. You should be careful about outliers, but you're okay to not worry about too much skewness in your data. So if you were doing the similar kind of example, right, using this data set, well, this is quiz 3, right? Except in quiz 3 you did it with the confidence interval. You did a hypothesis test without really knowing that you're doing a hypothesis test with a confidence interval. Here we want you to do it using an actual hypothesis test. So if I had all the data sets typed up here as the miles per gallon, okay, suppose I wanted to find out the mean, the standard deviation, and all that for the data set. I go to stat, basic statistic, display descriptive statistic. You select the variable that you want, so in our case miles per gallon, and if you want to choose what you want to see, then you can select them all here. The default options are fairly comprehensive. Okay, so you have the mean, the standard deviation, standard error, minimum, maximum, median, and all the quartiles, etc. Okay, so I'll just keep it at that. That's all I really need. So that gives me a mean of 28.8 and a standard deviation of 6.89. So now that I know that x bar is 28.8 and S equals 6.89, well, let me state my hypothesis. Mu equals to 27 and H1 is mu not equals to 27. Okay, it's just saying is it 27 or not. That or not tells you that it's just a not equals to. And we can then find out t statistic, right, x bar minus mu s over square root of n. That's 28.8 minus 27 divided by 6.89 over square root of 20. Okay, so just calculate that. 28.8 minus 27 divided by 6.89 by square root of 20. And you get 1.17. Now from Minitab, we get the p-value. So back to graph, probability distribution plot, right? View probability. Then we have our t-distribution. What's our degrees of freedom? We have 20 samples, right? So our degrees of freedom is 19 and minus 1. Go to shaded area. It is two-sided. And our value that we found is t is 1.17. And click OK. Okay, so on each side you have 0.13. When we add them up, you get 0.26. So our p-value is then 0.26. Okay, and since p-value is greater than alpha, right, an alpha of 0.05, we will fail to reject H0. Therefore, the test is inconclusive. We didn't learn anything. Right now, you would go out and get a better data set to maybe come up with some other conclusions. Okay, now let's see how to do this entire test in Minitab. Okay, so to do the test, you go to Stat, Basic Statistics. Now, just like we did the hand test with one sample Z, you can also do the same test in one sample Z. Here I'm going to show you for one sample T, and it's going to be exactly the same process as you would for one sample Z test. Previously we did it by hand. You can do the same thing by computer in Minitab also. But I'm just going to show you for T, and then you can practice on yourself by the Z. It's the same process. So for one sample T test that we just learned, you go to it. Now, if this is what it's going to look like. If your data is typed up in a column, then you select the first option and double click the data. If it is summarized for you in the form where you know the sample size, you know the sample mean x bar, and you know the sample standard deviation s, then you type them up there. Okay, here we have it in the column, so I'm just going to double click and select it there. You want to check the box that says perform hypothesis test, because that's what we're doing, and you want to put in your hypothesized value, which is your mu naught, right? What you're guessing. The mu equals to the number, that number here. You click on options. Here you can change the confidence level, but we're working with 95%. And you can select if you want it to be two-sided or one-sided. Here we're working with a two-sided value. So the mean not equals to hypothesized mean is a hypothesized alternate hypothesis. And then you click OK. And Minitab prints for you all this output. When you do the homework, make sure you copy from, if you're using Minitab, from the top line all the way to the bottom line and put it into the Word document. This shows me what test you used, and without that you won't get any points. Okay, so make sure you include this bit, and then of course the following bits which shows the output of the result. Okay, so then Minitab tells you, okay, this is a test on a hypothesis with the null hypothesis being mu equals to 27 versus not equals to 27. It tells sample size, mean, standard deviation. It gives you the 95% confidence interval. Okay, then this gives you t-stat. Okay, this is the t-stat value, t equals to 1.17, exactly what we found, if you remember. And then it gives you p-value of 0.26, just like we found it. And so based on that p-value, you can then make a conclusion that p-value is greater than alpha, and therefore we fail to reject. Okay, exactly the same steps as you would manually. This may be quicker, and again, you're free to use Minitab during your tests, your homeworks, and quizzes. Okay, let's move on. Okay, now we move on to proportions. So all this time we've been talking about mean hypothesis tests on means, right? So all this time it has been of the form H0 mu equals to mu 0 versus H1 mu equals to not equals to mu 0, or mu greater than mu 0, or mu less than mu 0. Right? Well, now we're going to shift focus and talk about proportions. So our hypothesis, H0, will be P equals to some value, P0, versus p not equals to some value p0, or p greater than some p0, or p less than some p0. Again, notice all the hypotheses are in terms of the population value, right? We talk about the mean, which is a population mean. We never know these values. So one takeaway that you should try to memorize is hypotheses are always stated using population parameters, never using sample statistics. You never put X bar in your hypothesis. You never put P hat, right? This is a population proportion, P. When you're talking about the sample, that's P hat. P hat is sample proportion. Never put that in the hypothesis. It's always in terms of population parameters. Okay, so now we want to do a hypothesis test for proportions. Turns out that the mean of the proportions, just like we had for X bar, the mean of the proportions will be along exactly down the middle, but the standard deviation of the proportions will have this setup, square root of p times 1 minus p over n. Right? So if you take many samples and compute proportions, just like we would for the mean, right? We took many samples and compute lots of different means, and then said the distribution of those means had a center at the population mean and had a spread of sigma over square root of n. Here we're saying the center is at the population proportion, and the spread is square root of p times 1 minus p over n. Okay. So for example, a survey found that 1,063 out of 2,054 adults said they played video games. Okay, you want to test a hypothesis if a certain conception that you have about how many people played video games is true or not. So the first thing you do is set up a hypothesis, okay, and you can set up an alternate hypothesis. Then you compute a z-stat. So for proportions, there is no t. Okay, it's always going to be using z distribution. And we'll say the only way you can use the z distribution is if your assumptions that n times p and n times 1 minus p has to be greater than 5. So that's your biggest assumption to check. N times p is greater than 5, and n times 1 minus p is greater than 5. And then once you find z-stat, then it's about finding probabilities based on that z-stat, exactly the same way as you did for the previous chapter or the section. Okay, so let's look at an example. A national survey by the National Institute of Occupational Safety and Health on our restaurant employees found that 75% said that the work stress had a negative impact on their personal lives. Investigate a restaurant chain to see if the proportion of all employees negatively affected work stress from the national proportion. So H naught is P equals to P naught, and P naught we know is 0.75, versus P not equals to P naught. It's two-sided. You're saying if it is equal to that value or not. You take 100 random samples, and you find that 68 of them said yes. Okay, so 32 said no. So first you check your assumptions. N times P Okay, p we had was 0.75. N times p is 75, that's greater than 5. And n times 1 minus p is 25. Right, 100 times 0.25 is 25. That's also greater than 5. So that assumption holds, so that's good. You can also put a constraint of 10. That's also fine. 5 usually is okay, but 10 makes it even more stronger. And then you compute the z statistic. Okay, so p hat is equal to, you had 68 of them said yes, so 68 divided by how many employees? 100. So this is 0.68. Now you put in p hat of 0.68, p naught of 0.75, put in p times 1 minus p divided by n, square root of that, and you get the z stat. Okay, and then you can go to Minitab and put in the value of 1.62, right? And we've practiced that many times now. You should be able to do it by yourself. You should put in a z value of 1.62 and find out that the p-value is equal to 0.11. Okay, and since p-value is greater than alpha, if alpha is 95%, we will fail to reject H naught. Okay, so that says the chain restaurant data are not significantly different, or more importantly, the test is inconclusive. You don't have enough information to really make a judgment, so go collect more information. Okay, and so again, we here compare the z statistic with the z critical, which is the same as comparing p-value with alpha. This table again shows you that it's the same thing when you're comparing z statistic with z critical and the p-value with alpha. Just make sure your assumptions hold for using the proportions test. So let's look at an example. In a survey of 1,430 undergraduate students, 1,087 said they had one or more credit cards. You want to compare this to a national average of 75 and see if that is true in Bowling Green or not. So, state your hypothesis. It's very easy to write mu right away, but we are talking about proportions, p. Okay, so we're testing if p is equal to 0.75 versus H1, which states p is not equal to 0.75. Okay, now check your assumptions. N times p, which is equal to 1,430 times 0.75, that is definitely much bigger than 5, and n times 1 minus p, which is equal to 1,430 times 0.25, is also much bigger than 5. So assumptions hold. Okay, so then you find z stat. Again, in the test you may have to state your assumptions. Okay, so make sure you check those and you state it. So now you find z stat, and that is p hat minus p naught divided by square root of p naught times 1 minus p naught over n. Right? Now p hat is 1087 over 1430 minus 0.75 all over square root of 0.75 times 0.25 divided by 14 30. Okay, and when you work that out, that turns out to be 0.89. Okay, and then you go to Minitab to find out the p-value. Right, so that's graph, probability distribution plot, view probability. We're back to the z-distribution, right? So normal with a mean of 0 and standard deviation of 1. Here we're given a z-value of 0.89, and it is two-sided, right? Two-sided. So we pick two sides, z-value of 0.89. Click OK. You got the two probabilities. You add them up, right? 0.19 plus 0.19 gives you 0.38. Right, so that gives us from Minitab, we get a p-value equals to 0.38, which is much bigger than alpha, therefore reject H0, which implies accept H1. And so BGSU does have a different average than the national average. Okay, so we have covered hypothesis testing on the mean, mu. We've covered hypothesis testing on the proportion, right? And now we're going to cover hypothesis testing on the variance, sigma squared, right? The population variance. For that, we have to learn a new distribution. So just like you had the normal distribution and the t-distribution, you're going to have to learn the chi-squared distribution. Okay? It's not pronounced chi, but it's pronounced chi. Chi-squared distribution. And this is the symbol chi. Okay, it's like a cursive X. And it has a square on it. So chi-squared distribution. The thing to take away from the chi-square distribution is that it is only one-sided. It's not symmetric. Okay, it only has values in the positive direction. Okay, so take away chi-squared distribution is skewed to right, only has positive values. Okay, you can see that it's skewed to the right, and it's dependent on the degrees of freedom. Okay, so chi-square distribution is also, just like the t-distribution, dependent on degrees of freedom, which is n-1. Okay, and you can see that how the shape changes of the distribution based on sample size or the degrees of freedom. So here n equals degrees of freedom equals to 2, so n equals to 3. Here n equals to 6. Here n equals to 11. Right? And so the degrees of freedom shows you how the shape of the distribution changes. Okay, and so we can compute the chi-squared statistic as the following. It's n-1, so sample size minus 1, times by the sample standard deviation divided by your hypothesized population standard deviation. Right? So remember, your first thing you do is set up your hypothesis. Okay, H0 is such that sigma squared, which is your variance, is equal to some value. And you typically denote that we're going to just be generic and denote it as sigma squared naught, right? Just like we've been doing for mu naught and p naught. And your alternative hypothesis is sigma squared is not equal to sigma squared naught, right? Or is sigma squared greater than sigma squared naught? Or sigma squared less than sigma squared naught, right? Any of those can be alternate hypothesis, two-sided or one-sided. Okay. And then you compute chi-squared statistic. Okay, and once you do, then you go to Minitab, find p-value using, and here you have to be careful, not the z or the t, but the chi-squared distribution. Okay, and you can compute a confidence interval Ci as this formula. Again, this is given on a formula sheet. During test, you will have access to it. Or you can use Minitab. Right, it's sample size minus 1 times the sample variance divided by the chi-squared critical value. And on the right-hand side, it's chi-squared 1 minus alpha over 2. That's the critical value. Or you can just compute chi-squared statistic using this setup, then find p-value, and make your conclusion. Okay, so let's look at a practice question. A company's machines produces parts with standard deviation 2.4, which is sigma. Right? Sigma. You take a sample of 20 parts from your favorite machine. That has a mean of 11.3, so that's x bar, and a standard deviation of 1.9, so that's S, right? Sample standard deviation. Is the variance in parts from your favorite machine same as the rest of the companies? So set up your hypothesis. Okay, that says that the variance is equal to .4 2.4 squared, right? Because that's just the standard deviation, versus H1 that says the variance is not equals to 2.4. Okay, and then we compute chi-squared statistic, right? That's n minus 1 times by s squared divided by the hypothesized variance, right? So we had n minus 1 is 19 times s squared, which is 1.9 squared, divided by our hypothesized variance, which is 2.4 squared. So that 1.9 squared times 19 divided by 2.4 squared comes out to be 11.91. And then we go to Minitab to find the p-value. Okay, once we're in Minitab, we go to graph, probability distribution plot, view probability. Now we want it to be chi-squared, right? That's what we have, the chi-squared distribution. And the degrees of freedom is 19, right? 20 minus 1, 19. We want shaded area. Okay, for chi-squared, always pick the right-hand side. Okay. For two-sided tests, you want to pick the right-hand side, put in the chi-squared value, 11.91. And here's where it gets a little tricky. You have to use the smaller of the probabilities that's selected for you. Remember, chi-squared is not symmetric. Even though this looks symmetric, it is not symmetric. You can see the right-hand side is skewed a little bit. They're all positive values, right? Zeros out here. So you have to pick, when it's two-sided, okay? When it's two-sided, you have to pick the smaller value. So you want this area, okay, which is 0.11, because this is 0.89, right? This whole area is 0.89, so 89%, so 11% is left over. Okay, and once you find the smaller area, this is only for two-sided. Once you find the smaller area, then you multiply it by 2. So 11 times 2 is 22. So that becomes your p-value in this exercise. Okay, so then p-value equals 0.22 because it's two-sided. Okay, if it had been one-sided, right? If it had been one-sided, then you would pick the side that you are dealing with. If it was greater than, you would pick that. If it was less than, you would pick that, and you would get 11% on the left-hand side. Okay, and if it was greater than, you would get 80 or 88%, right? Just like we did before. But here you have to, once you find that smaller probability, you got to multiply it by 2 because it is two-sided for chi-squared. Okay, now let's see how to do all of this by Minitab. So if we go to Stat, Basic Statistics, and then one variance. It's a one variance test that we're doing, okay? Now using the drop-down menu, we're typically always going to use this summarized information, okay? We have either the sample standard deviation or sample variance, whatever you want to put in. I just put in what's given in the question, and that is standard deviations are given. So S is given and sigma is given. So my sample standard deviations are given, sample size is 20, and my sample standard deviation is 1.9. I want to do a hypothesis test where my hypothesized standard deviation is 2.4. Remember, this was the sigma naught, right? This was the sigma naught that we had. And this was sigma naught. Okay, and so going back here, you can change under options if you want it to be one-sided, but we want it to be two-sided. We click OK, and we get this output. You have your confidence interval, and it tells you what method, which is the chi-squared, and it tells you the p-value, 0.22. Right? And if we go back and look at our answers, see, we got 0.22. And the chi-squared value is 11.91, just like Minitab says, 11.91. Okay, so you can, in fact, do this in Minitab. Okay, and since we got a p-value of 0.22, that means that p-value is greater than alpha. Therefore, fail to reject. H naught. Therefore, test is inconclusive. Okay, so this table summarizes, again, you can pause it right here. This table summarizes, again, you can compare the chi-squared statistic with the chi-squared critical, okay, or you can compare p-value. And here I've put in a note that when you're doing a two-sided test, like here, this is all for two-sided, you find the area to the right and area to the left of the chi-squared value, okay? And you pick the smallest one, okay? A is the area to the right of chi-squared or the area to the left of chi-squared, okay? So that and that. In our case, one was 89%, the other was 11%. You pick whichever is smaller, so the 11%, and you multiply it by 2 to get the p-value. If it's one-sided, you just choose that side, the left-hand side or the right-hand side, based on what your sign is. Okay, that brings an end to this chapter. Again, please make sure you're following along with the quizzes. You're doing the quizzes, you're also doing the homeworks. All the due dates are posted. You should be able to do all the materials in the class in this course based on what you've learned from these videos. Again, if you have any questions, feel free to call me at my office number, which is listed on the syllabus, or also leave me a message on email at aroy@bgsu.edu, and I'll get back to you as soon as possible. Thanks.